Well, hello there. This is Osama Al-Amrani. I am a grade 11 student at Al-Nada School in Sana'a, Yemen. In this episode, we'll make a quick review of the periodic table. Let's talk about something truly elemental, the periodic table. Imagine you have a library, but instead of books, it's filled with every single type of stuff in the universe. How would you organize it? By color? By weight? The periodic table is science's brilliant way of organizing all the elements, the basic building blocks of everything you see, touch, and are. It's more than just a chart on a classroom wall. It's a map to the cosmos, a cheat sheet for chemists, and a powerful tool that predicts how different kinds of matter will behave. From the hydrogen in the stars to the oxygen you're breathing right now, every element has its own special place. So, how is this magnificent chart arranged? It all comes down to one little number, the atomic number. This number tells you how many protons are in the nucleus of a single atom of an element. Hydrogen has an atomic number of 1 because it has 1 proton. Helium is next with 2 protons, so its atomic number is 2. The table reads just like a book, from left to right, top to bottom, in order of increasing atomic number. This simple, elegant organization is the key to everything. It's what groups elements with similar personalities or chemical properties together. This order isn't random. It reveals a deep, underlying pattern in the very fabric of nature. Now let's get to the real action heroes of the atomic world. Valence electrons. These are the electrons in the outermost shell, or energy level, of an atom. Think of them as the atom's hands that it uses to interact, bond, and react with other atoms. The number of valence electrons an element has determines its chemical personality. For example, elements in the first column, like sodium, have just 1 valence electron, making them very eager to give it away. Elements in the last column, the noble gases like neon, have a full outer shell of 8 valence electrons, making them stable, content, and generally unreactive. They're the cool kids who don't need to join any clubs. The importance of these valence electrons cannot be overstated. They are the reason chemistry happens. When sodium, with its 1 lonely valence electron, meets chlorine, which has 7 and desperately wants 1 more to complete its shell, a chemical reaction is inevitable. Sodium happily gives its electron to chlorine, forming a strong bond and creating sodium chloride, table salt. This desire to have a full outer shell, known as the octet rule, drives almost all chemical bonding. Understanding valence electrons is like having the secret handshake to get into the exclusive club of chemical reactions. It's all about an atom's quest for stability. Let's talk about size. Atomic size, that is. The atomic radius is basically the distance from the center of an atom's nucleus to its outermost electron shell. You might think that as you add more protons and electrons, atoms would just get bigger and bigger, right? Well, it's a bit more complicated and way more interesting than that. The size of an atom changes in a very predictable pattern across the periodic table, and it creates fascinating trends. This pattern helps us understand how atoms will interact with each other. It's like knowing the reach of a boxer before they even step into the ring. As you move down a column or a group on the periodic table, atoms get bigger. This one makes perfect sense. Each time you step down a row, you're adding a whole new electron shell, or energy level. Think of it like adding another layer to an onion. Lithium in the second row has 2 electron shells. Go down to sodium in the third row, and it has 3 shells. Go down again to potassium in the fourth row, and it has 4 shells. More shells mean the outermost electrons are farther from the nucleus, so the atom's radius increases. It's a straightforward expansion, layer by layer. But here's where it gets a little counterintuitive. As you move from left to right across a row or a period, atoms actually get smaller. How can that be? You're adding more protons to the nucleus and more electrons to the same outer shell. The key is the increasing positive charge of the nucleus. As you add more protons, the nucleus becomes more powerfully positive, pulling all the electrons, including those in the outer shell, closer to the center. It's like upgrading the magnet in the middle. It tugs everything inward with greater force, shrinking the atom's overall size. So let's put it all together with an example. Consider sodium and magnesium. They are both in the third period. Sodium has 11 protons, and magnesium has 12. Because magnesium's nucleus has a stronger positive charge, it pulls its electron shells in tighter than sodium does, making the magnesium atom smaller, even though it's technically heavier. Now, compare sodium with potassium, which is directly below it. Potassium has an entire extra electron shell, making it significantly larger than sodium. The biggest atoms are in the bottom left corner, and the smallest are in the top right. Consider it. Now let's talk about energy, specifically the energy it takes to mess with an atom's electrons. Ionization energy is the amount of energy required to completely remove one electron from a neutral atom. Think of it as the atom's grip on its outermost electron. If an atom has a very strong grip, you'll need a lot of energy to pry that electron away. If the grip is weak, it doesn't take much effort at all. This property is crucial because it tells us how likely an atom is to form a positive ion by losing an electron, a fundamental step in many chemical reactions. The trend for ionization energy is essentially the opposite of the atomic radius trend. As you move from left to right across a period, the ionization energy generally increases. Why? Because as we learned, atoms get smaller and the nucleus's positive charge gets stronger. That stronger pull from the nucleus holds onto the outer electrons more tightly, making them much harder to remove. For example, it takes a lot more energy to remove an electron from fluorine than it does from lithium, which is on the far left of the same period. Lithium is practically begging to give its electron away. Conversely, as you move down a group, the ionization energy decreases. This is because the atoms are getting larger, with more electron shells. The outermost electron is much farther from the nucleus and is shielded by all the inner electrons. This electron shielding effect weakens the nucleus's pull on that valence electron, making it easier to pluck off. For instance, it's easier to remove an electron from potassium than from sodium above it, because potassium's valence electron is one shell farther away from the nucleus's attractive force. It's like trying to hold on to a balloon on a very, very long string on a windy day. On the flip side of losing an electron is gaining one, and that's where electron affinity comes in. Electron affinity is the energy change that occurs when a neutral atom gains an electron. For most elements, this process releases energy, so we talk about it as a measure of how much an atom wants an electron. Generally, elements on the right side of the table, like the halogens, fluorine and chlorine, have a high electron affinity. They are just one electron away from a full stable shell, so they will eagerly accept an electron to complete their set, releasing a good amount of energy in the process. Consider chlorine, which has a very high electron affinity, readily grabbing an electron to become a chloride ion. So, atoms can lose electrons or gain them, but what happens when they share? That's where electronegativity comes in. Electronegativity is a measure of an atom's ability to attract shared electrons to itself when it's part of a chemical bond. It's not about taking an electron completely, but about who wins the tug-of-war over the electrons being shared between two atoms. An atom with high electronegativity is like an electron bully. It pulls the shared electrons closer to its own nucleus, hogging them. This concept is one of the most important for predicting how atoms will bond together. The trend for electronegativity is very clear and easy to remember. It increases as you go from left to right across a period and decreases as you go down a group. The most electronegative element of all is fluorine, located in the top right corner of the table. Though we don't count the noble gases because they rarely form bonds. Fluorine is small and has a powerful nucleus, giving it an incredible pull on electrons. On the other end of the spectrum, you have elements like francium in the bottom left corner. These elements are highly electropositive, meaning they have very low electronegativity and are very likely to give up their electrons rather than attract them. Let's look at a classic example. A water molecule. Oxygen is much more electronegative than hydrogen. When they bond, they share electrons, but it's not an equal sharing. The highly electronegative oxygen atom pulls the shared electrons closer to itself. This makes the oxygen side of the molecule slightly negative and the hydrogen side slightly positive. This uneven sharing or polar bond is what makes water such a fantastic solvent and gives it all its amazing life-sustaining properties. It's all because of a difference in the electronegativity tug-of-war. In conclusion, the periodic table isn't just a collection of squares and letters. It's a story of cosmic order, revealing the fundamental rules that govern all matter. By understanding how properties like atomic number, valence electrons, atomic size, ionization energy, and electronegativity change across the table, we unlock the secrets of chemistry. We can predict how elements will behave, how they will bond, and what kinds of amazing substances they can create. From the salt on your fries to the water you drink, the principles laid out in this beautiful chart explain the world around us. So go on, explore it. Science is all around you.